So this is IBDP HL acid bases part. In this chapter, in the acid bases chapter, we have to learn that what exactly is the acid and what exactly is a base. Now, before going to this part, right? We have to know a little bit of theory, which the painstaking scientists they took around how many years back? Around 300 years back, right? It was very painstaking, right? What happened? Acids, they tasted acid, right? They tasted acids. Base, they did what? Base, they actually felt it, right? Felt it. They tasted acid. They told that acids are those which will be having a sour taste, right? Is it clear? Did you get it? What are bases? Bases, they felt the touch. Anything slippery, that is a base, right? Isn't it? Right? Did you understand this part? What I'm saying? But isn't it a very risky way? Isn't it? You taste acid, right? We taste acid, isn't it? Isn't it a very actually risky way? Yes, it's a very risky way, right? Not an easy way. We taste acid, right? It's a very risky way. Bases are felt by the touch, right? This is very important, right? We feel by the base of the by the touch. Anything slippery is called as a base. Now going to the next part, now we have to understand that if you're seeing the one of the most, this is the way around 1770 this was approached. It was a painstaking process. Now a very important theory came into the picture when what? In 1890, right? The scientist called Arrhenius, right? He was a brilliant scientist, right? Arrhenius. Arrhenius told what? Came up with this theory of the acid bases, right? He told what? He told that acids are those, right? He told that acids are those which when dissolved in water, right? Acids are those substances, right? Did you hear me this? Acids are those substances which when dissolved in water, right? You have to dissolve something in water, right? Acids are what? Acids are those substances which when dissolved in water, right? They will be dissociating to what? They'll be dissociating into H plus and A minus, right? Isn't it? So he said what? He said that acids are those which when dissolved in water, acids are those substances which when dissolved in H2O, water, they will be giving you H plus and a A minus, right? Isn't it? And what did he told about the told about what called the bases? Bases are those which when dissolved in water. See, bases are those which when dissolved in water. They'll be giving you what? They'll be giving you a P plus and OH minus, right? Isn't it? So this is a very important part for you to know. Arrhenius theory was very close to the theory which we study now, right? Very close to the theory which we studied now. And this is widely accepted, right? Was really appreciated. But this theory was very close, but he made a little bit of mistake, right? He took only aqueous solution, right? This is the thing, right? Only aqueous solution was taken, H2O solution was taken. So this is very crucial for us to understand that whenever we are seeing acids, acids are those substances which when dissolved in water gives you a H plus and a A minus. Bases are those substances which when dissolved in water will you B plus and a OH minus, right? Now always remember over here that this H plus, right? H plus is the main player of the acidity, right? Is it clear? Fine. And what is the OH minus? OH minus is the main player of the basicity, right? So this is the way we have to know. Now, do you know what? There are many bases. Now you can write it down also that bases are what? Please write it down, right? In the chemistry school copy. Bases are can be metal oxides, right? Can be metal hydroxide, right? Please note this down. Can be metal carbonates. Please write this down, right? Can be metal bicarbonates, right? See, Na2O base, right? Metal hydroxide, NaOH, see, base. Metal carbonate, see, calcium carbonate, base. Metal bicarbonate, calcium bicarbonate, HCO3, right? Isn't it? So this is very crucial for us to know that whenever we are seeing the bases can be metal oxides, metal hydroxide, metal carbonates, and metal bicarbonates, right? Now coming to this thing, now the main thing is that the Arrhenius already delved deeper into the aqueous system. He told about the aqueous system. But you know what? But there are many aqueous system, right? Suppose there are many bases. Suppose calcium oxide and calcium carbonate, right? Are they soluble in H2O water? No, they're not soluble in H2. Is it clear to you? So what about these, right? What about these? These are not soluble in H2, right? So this is very important that whenever we are taking this theory, the theory was very close to the theory which we study. He improvised and he revolutionized the entire theory. But there are many bases which are not soluble in water. He took aqueous medium, right? There are many bases which are not soluble in water. What about those? What about those? which we won't be able to fit into the theory to it because you need aqueous medium. That's the reason. This just small reason was the thing that his theory was improvised. Many years later, of approximately 30 years later, what happened? After 30 years, we'll be seeing that there was a scientist called as what? There was a scientist called as two scientists, Bronsted, Bronsted and Lowry. Please connect with a pen also, right? If you have got an eye pen, please connect your pen. The Bronsted-Lowry theory, what happens? So in the Bronsted-Lowry theory, it's almost what after Arrhenius theory, right? Two scientists, right, which was Bronsted and Lowry. They came across a very important simple theory. They simplified the way by which we think acid bases, right? He told what? He told that acids are what? Acids are proton donors. Simple, right? It was simple. Acids are proton donors. What are bases? Bases are proton acceptors. Makes sense, right? It's very simple, right? He revolutionized this. This theory is the theory we just studied till now also, right? Isn't it? So Bronsted-Lowry, the main theory is what? Acids are proton donors, right? Bases are proton acceptors. So it's very simple, right? Isn't it? Suppose we are seeing this. Suppose we are trying to see this example. Suppose over here. Okay. Now, if you see that whenever we are seeing an acid and a base, right? The theory is what? Acids are proton donors, right? These are proton donors. Bases are proton acceptors, right? What happens? Suppose you're adding HCl to ammonia, right? What happens? You're getting NH4 plus. What exactly happens over here? We are seeing that over here, the H plus, right? The H plus, right? Here, the H plus is going and getting connected with the ammonia, right? Isn't it? What happened over here? Can you guide me? Over here, we are seeing that this HCl donated a proton, right? Donated a proton, right? Isn't it? And this ammonia, what did it do? This ammonia accepted a proton, isn't it? Did you understand this thing? Accepted a proton. So this is very crucial for us to understand that whenever we are seeing acid-base theory, it simplified the thing, right? Now come to this thing. Now we have to understand that when we had discussed earlier in your IBDP chapter number 3, right? We discussed what? We also discussed that if suppose we have sodium is 281 and chlorine is what? 287, right? Isn't it? Now, if suppose sodium, if you take, right, sodium has got an electronic configuration of 281, isn't it? Means you can write like this also: 1s2, 2s2, 2p6, 3s1, right? Isn't it? In this. So over here we have to know that sodium and all the elements, right? All the elements which are there in the entire periodic table, they have got only one mission in their life. What? They have to get the noble gas configuration, right? So in that process, now tell me one thing. Over here, what happens? Over here, we are seeing that sodium has got one electron in the outermost orbit. They have to drastically, they have to dispose of this electron, right? They have to get rid of the electron. Now here comes the catch. Sodium wants to dispose this electron and gain noble gas configuration 2,8, making Na plus, right? Now remember one thing, as we learned in the earlier chapter also, that if sodium wants to lose an electron, right, it cannot lose the electron in isolation. Is it clear? Cannot lose in isolation. It has to find out somebody who can gain that electron. That's very simple, right? So in that process, what happens? In that process, we'll be seeing that sodium will be transferring an electron to chlorine. If chlorine is near it, if chlorine is near it, if chlorine is near it, it cannot just dump this electron, isn't it? Similarly, if chlorine has got 287, it desperately wants one electron, right? But it cannot just take out an electron which is lying idle, right? Electrons are not like that. Means somebody has to give the electron to chlorine. So this is very crucial, that whenever we are seeing this reaction, right, sodium has to find somebody to give that electron, and chlorine has to find out somebody who can give that electron to. Similarly, in that same base, we have to know that if you're seeing that we are having an acid, HCl. HCl alone cannot just donate this proton. Is it clear? Cannot dump this proton. Not. It has to have somebody who can accept the proton. Did you get this thing clearly? So this is very crucial for us to understand that whenever we are seeing HCl, HCl cannot be dumping a proton on its own. Means HCl cannot just dump the proton in isolation. It has to have somebody who can accept the proton. Now comes the basic of what? Many important part, that there should be a what? There should be a base. in very close proximity to acid, so that the acid can give that proton. Acids are proton donors and bases are proton acceptors who can accept. So obviously you have to have a base for an acid to exhibit its acidic properties. It's very simple, right? Similarly, vice versa also, if there's a base which is there, a base accepts a proton. It cannot just take out a proton from anywhere, right? It has to have an acid near it to give that proton, right? So hence we come across what? Hence we come across a very important theory which is called as what? Called as the conjugates, right? Now, how do the conjugates look like, right? Now see. Now, if you see that when we are seeing this reaction, right? HA plus B, right, gives you A minus plus BH plus. Now connect with the pen. I'll be asking questions. So if you see this reaction, right? What did I tell you? Acid cannot act in isolation. It has to have a base where it can give that proton. Bases are proton acceptors. Similarly, bases cannot act in isolation. It have to have an acid which it can get an proton from. Then comes the concept of what? Then comes the concept of conjugates. Suppose we are taking acid HA plus B gives you A minus plus BH plus, right? Now we have to go to the boxes, right? Isn't it? We have to draw the boxes. This boxes will be very crucial. Draw the boxes, that will be easy. Now, in the first reaction, what happens? Can you see this? This HA is actually donating a proton to B, isn't it? Donating a proton to B. Okay, that's great. When it is donating a proton to B, what happens? Over here, HA is donating a proton and is going to where? Going to A minus, right? Now, we can write down now over here acid, then B, below B we write base, right? Over here, base. Makes sense? Now, going to the back reaction, what happens? Going to the back reaction, BH plus came from where? You have to see that BH plus came from the base, isn't it? This, right? BH plus came from the base, right? After it accepted a proton, isn't it? Acid HA was donating a proton. It donated a proton and given A minus, right? Base B will be accepting a proton from HA over here like this. It accepts a proton and it goes where? It goes to BH plus. So this is very interesting that in the back reaction, can you guide me that who acts as the base, who acts as the acid? Can you guide me? In the back reaction, see, you have to follow that what is happening over here. In the back reaction, you can see that this is the reaction, right? Wonderful answer. Wonderful answer. Wonderful. And base, write down. Where's the base? Let me just rub this off so that you can get. Yes. Perfect. I'm really wonderful answer, right? Yes. So in the back reaction, we can say that this is acting as the acid. But this acid came from where? This acid came from the base, right? So this is called as what? This is called as the conjugate acid of the base. Is it clear? Simple. And we are getting what over here? We are getting over, this is the base. Now base comes from where? Base comes from the acid. So this base is called as a conjugate base of this acid, right? Isn't it? So this becomes a very important part of conjugates. And these conjugates will be carrying on to your entire HL journey, I'm telling you. It will be a very important part you have to master, right? Isn't it? So we know very well that this and this is what? This is this. What? This is the acid and its conjugate base pair, right? Is it? Acid and the conjugate base, right? What this you're getting? This is a base and conjugate acid pair. So we write like this: base oblique conjugate acid pair, right? Is it clear? This is the way you write, right? So can you tell me one thing? That if we see this acid, right? If we see this acid and if we see this conjugate base, right? What are they differing in? Can you just tell me? What are they differing? See, HA and A minus. Now, this is very important that whenever we are seeing HA and A minus, right? This is the acid and the conjugate base of this, right? So always remember that the conjugate acid and the conjugate base will be differing by what? Can you guide me? Can you just write on the screen, please? Thank you. What they're differing? Tell me. By H plus ion. Very good. So this is very important. They differ by a H plus ion. So this is very crucial for us to know that whenever we are seeing a conjugate acid base pair, right? They will be differing by H plus ion. Similarly, over here we are seeing that B and BH plus. This is also differing by H plus ions, right? So we come to the conclusion that conjugate acid base pair, they will be differing by H plus ion, right? Only. And conjugate acid and conjugate base pair, right? So sorry, acid and a conjugate base pair, right? They'll be differing by H plus ion only, right? So, so this is what? This is the portion of what? The conjugates, right? Let's do what? You have to know some important points over here, right? We have to know that conjugate bases come from where? Conjugate bases come from a acid, right? Isn't it? Acid. Always remember this thing, right? And conjugate acids come from where? Conjugate acids will be coming from a base, isn't it? So this is very crucial, right? Conjugate acids come from a base and conjugate bases come from an acid. This is a very, very important part, right? You have to remember, right? To answer questions which are coming up, right? The questions will be really tricky, right? Will be really tricky, right? That suppose I'm giving you a question now. Suppose we are trying to take this, suppose over here. So the question is that, suppose write down the conjugate base for each of the following, right? Suppose they're asking you that write down the conjugate base, of NH3, right? Now there's a request now over here to all my students, right? That always do not, when you're handling this question in A levels or in IBDP, right? This question is a very common question. What is the conjugate base of ammonia? Never ever quantify this, right? This is very important. Never ever try to quantify this, right? That what exactly is it acid or a base? Never ever, right? Ammonia is a weak base, right? So never ever tag it, right? Because we know that conjugate base of ammonia, right? When you learn that conjugate base of ammonia, now to learn that conjugate bases come from where? Conjugate bases, we'll just like this. Conjugate bases come from a acid, right? Isn't it? Conjugate base come from acid. So obviously, this will be behaving as a acid. See, our entire tagging will be under threat, right? Ammonia is a weak base, but we have to know the question also. What's the conjugate base of ammonia? So ammonia is behaving as an acid. Now, what does the acid do? Now, if you write like this, what does the acid do? Right, ammonia. Acid will be donating a proton, right? Donating a proton. So this is very important that whenever we are saying that acids are donating a proton, right? So obviously, now this is the skill you have to learn, right? Is donate a proton, so minus H plus, right? Isn't it? Now over here, what we do, when we want to find out that what the conjugate base, right? After it donated a proton, we have to subtract the elements, isn't it? So nitrogen, hydrogen is H3 and H is getting subtracted. Subtract the elements first, NH2. Then over here, what do you do? Over here, we have to do what? Over here, we have to see that this charge and this charge. Now remember this thing, right? This trick. This charge and this charge will be equal to this, right? That is 0, right? Isn't it? So can you tell me that what will be the charge of this per NH2? Can you guide me? The charge of this NH2? Tell me. This will be plus X is equal to 0, right? See, this plus this, right, will be equal to 0, right? Isn't it? So this plus 1 plus X equal to 0 or X is equal to minus 1. Did you get this trick? Just remember this thing, when you're subtracting a proton, not adding a proton. When you're subtracting a proton, first try to subtract the elements. We get it, right? Isn't it? Then you have to do what? Then you have to make sure that this charge and this charge will be adding up to this charge, right? Isn't it? So this is very important that whenever we are seeing that what is the write on the conjugate base of ammonia. So we have to take this conjugate bases come from an acid. So this behaves as an acid, right? Is it clear? So this is very crucial going the line. Now, if you see that whenever we are seeing this reaction, right? Whenever we are seeing this reaction, we can easily follow the steps and go along, right? Now come to the second part of the question. The second part of the question comes from where? Write down what is or the question like to write down the conjugate acid, right? The conjugate acid of, suppose they give you CO3 minus, right? See, CO3 carbonate ion, right? Write down the conjugate acid of CO3 minus. In this part, you have to understand that whenever we are writing this, write down the conjugate acid of CO3 minus. How does it work? Conjugate acid, right? Now can you write down that what is this species? Conjugate acids come from where? Can you write down? Conjugate acids come from where? Can you write down? Conjugate acids come from a, tell me, a base. Brilliant answer. See, so brilliant, brilliant. So this will be acting as a base. So immediately write down the over here base. Then you write CO3 2 minus, right? This, right? Isn't it? Now, what does the base do? We have to immediately ascertain. A base will be proton acceptor, right? So we write proton acceptors, right? A base is a proton acceptor. So what it does? It accepts a proton. You write what? Plus H plus, right? Isn't it? Fine. It accepts a proton, right? H plus, right? Isn't it? Plus H plus. So when it accepts a proton, what happens? You're seeing that CO3 2 minus, right? CO3 2 minus plus H plus. What do you get? You first write down the elements added, right? HCO3. Then you see this charge and this charge. See, you're adding a proton. So this charge and this charge will be equal to this charge. So -2. Can you tell me that what will the charge over here? You add -2 and +1. What is the charge you're getting? Can you write down quickly? Thank you. Please write down over here. -1. Brilliant. So this is what? This is the conjugate acid, right? Isn't it? So this is very crucial for us to know that whenever we are seeing this, right? Conjugate acids, right? Of a species, they are bases, right? And we have to bases accept a proton as per Bronsted-Lowry theory, and we have to add the acid H plus, right? So this was what? This was about the all the theories which we came out. That we started with the initial theory, which was very risky, right? 200-300 years back. Then came Arrhenius theory, right? Isn't it? So that revolutionized the part. Arrhenius theory told what? That acids are those substances which, when dissolved in water, gives you a H plus and a A minus, right? Bases are those which, when dissolved in water, right, gives you what? A B plus and a OH minus. So this is very important. That theory was very short to the theory which we learn now, but it all took the cases of aqueous solution. There are many bases such as calcium oxide, calcium carbonate, which does not dissolve, right, in water. So we cannot be defined by this theory. So then came Bronsted-Lowry, right? That acids are proton donors and bases are proton acceptors. And that corollary we got into what? Into the conjugates, right? So this was what? This was very interesting part, right? Isn't it?